This video is a continuation of the experiments outlined in the first, in vivo fluorescence video. There, we discuss sources of background signal, including chow and tissue autofluorescence, and the appropriate control groups that are key to a successful in vivo imaging experiment. We also demonstrate how to set up fluorescence experiments using the imaging wizard. We look at how to image two probes in the same animal using a different excitation and emission filter pair for each probe, and how to check for crosstalk between the imaging channels. In this video, we look at how to use spectral unmixing to separate two or more fluorescent signals that have significant spectral overlap. Spectral unmixing is an image acquisition technique that can separate signals coming from two or more sources. When signals have significant spectral overlap, filters cannot be used to isolate each signal. Therefore, spectral unmixing must be used. The two most common scenarios where spectral unmixing is helpful is when tissue background is high, or when using two probes that have significant spectral overlap, usually less than 70 nanometers in separation. Spectral unmixing separates multiple spectra that might be mixed in vivo, in vitro, or ex vivo in a pixel-by-pixel manner. To accomplish this, images are acquired at multiple wavelengths. In this case, we scan from 680 to 840 nanometers. Pixels from the acquired images are mapped and grouped based on their spectral profile or signature. These grouped pixels are then separated into individual components so that accurate quantitation can be performed. This imaging approach can improve fluorescence imaging outcomes, firstly, by increasing signal-to-noise ratios, thus allowing detection of lower intensity sources. Tissue autofluorescence has a defined spectral signature and can be unmixed from probes, effectively resulting in background subtraction. After background removal, detection of signals that were previously masked by autofluorescence is now possible, since the signal-to-noise ratios have been improved. In this case, 3 concentrations of subcutaneous doxorubicin, a fluorescent molecule, were not visible when monochromatic or single filter pair imaging was performed. The signal-to-noise ratio was at or below 1. Spectral unmixing removed background, increased signal-to-noise, and allowed visualization and detection of the probe. Removal of background also improves quantitation. Here, probe concentration versus intensity is plotted. When the background is removed, there is more linear correlation between concentration and probe intensity. Lastly, spectral unmixing can help resolve signal from probes with overlapping excitation and emission curves. Spectral unmixing can accurately determine and separate the percentage of a pixel's intensity into spectral components, allowing for accurate quantitation and multiplexing, even into the near-infrared. Even small shifts can be detected, as shown here. 5 near-infrared probes were separated and independently displayed. Let's move on to the experimental design of our second in vivo fluorescence imaging study. In the previous study, we imaged 2 probes with 70 nanometer separation in their emission spectra. We had a 680 and a 750 nanometer probe. Here we will image 2 probes that emit at much closer wavelengths. To demonstrate spectral unmixing using the previously described 4T1 breast cancer model, we will replace our IvaSense integrin receptor probe from one that emits at 750 nanometers to one that emits at 645 nanometers. Now, there is only 35 nanometers in separation between the probes and much greater spectral overlap. The vertical bars represent the optimal bandpass filters for each probe. It will not be possible to use bandpass filters to capture the light from one probe without also capturing light from the other probe, given their high degree of overlap. Furthermore, the 645 nanometer probe overlaps more with tissue autofluorescence, so background signal from the tissue is expected to be higher at the lower visible wavelengths. Removing background will increase signal-to-noise ratios and allow more sensitive detection of sources. The first step in spectral unmixing is to generate a library from known controls. After generating the library, we can apply it to test animals that contain a mixture of probes to separate the signals. Saved libraries can be reused in subsequent time points of a longitudinal study. A library can also be reused in later imaging studies where the probes, mouse strain, and filter selections are the same. Using our animal model, we will generate a library for the 645 and 680 probes and apply it to a study. We will demonstrate best practices for acquisition and analysis of these datasets. Let's move on to the experimental design and acquisition setup. The design will be as follows. Mouse 1 will be a naive control animal bearing tumors in the mammary fat pad but receiving no probe injections. Signal in this mouse will show us tissue autofluorescence. Mouse 2 will be a negative control with no tumor but with both probes injected. Signal in this mouse will show us any off-target probe accumulation and probe clearance routes. Mouse 3 will be a positive control. The mouse has tumors and is injected with only the IvaSense pancathepsin 680 probe. Mouse 4 will also be a positive control. The mouse has tumors and is injected with only the IvaSense integrin receptor 645 probe. Mouse 5 is our last positive control. The mouse has tumors and is injected with both probes. We will inject these agents into our mice intravenously through the tail vein and image fluorescent activity at 24 hours post-injection following the recommendations in the probe datasheets. After the recommended 24-hour wait, follow the procedures for software launch, anesthesia setup, and instrument initialization as described in our previous videos. Anesthetize all 5 animals and then transfer them to the heated stage in the IVUS. Select the Imaging Wizard in the control panel. Choose Fluorescence, Spectral Unmixing, Epi-illumination, and then click Next. As a default, the wizard will set up acquisitions for 1 probe. To add a second probe, click the Add button on the right-hand side of the window. If your probes are pre-programmed in the software, you can choose them from the drop-down menu. If not, you can manually enter the input excitation and emission maxima, and the software will choose the appropriate filters for you. Click Next. Complete the last window of the wizard to include your imaging subject, auto or manual acquisition settings, and your desired field of view. Then click Next. The sequence editor will open and each filter pair selected will represent 1 image in the sequence. In this example, 12 images will be captured sequentially. Click Acquire Sequence. Label your images appropriately. Once the instrument has finished acquisition, the status light on the outside of the instrument will turn green. Remove the animals from the instrument and return them to their cages. Using this acquired dataset, we will now generate our spectral libraries. It is often useful to see the excitation and emission filters used for each image. To display the filters on top of the images, click the Options button, then select Display and Excitation and Emission Filters. Apply the Adaptive Fluorescence Background Subtraction Correction from the Corrections tab in the Tool palette. The calibrated unit we use for analysis is called Radiant Efficiency. Select the unit from the upper left-hand corner of the image window. We are now ready to create the spectral library. Open the Spectral Unmixing tab in the Tool palette. You will see all combinations of excitation and emission filters that were used to take the images in the sequence. If any saturated images exist, they will be deselected automatically. Spectral unmixing can be performed several ways. The different methods can be seen at the bottom of the tool palette. In this video, we will use the manual method to create and save our library. When we image our test mice, we will select Library and choose the library we just created using our control mice. Click Start Unmixing. The image window will display with 3 sections. First is the Large Image Cube Viewer. It is essentially a Z-stack of all images from the sequence superimposed onto each other. To view individual images, uncheck the Overview box. The second is the Spectral Graph on the top left. It shows the average intensity as a line for a pixel or group of pixels throughout the emission scan or Z-stack. The spectrum list on the bottom left contains drawing tools for selection of pixels that will be utilized to generate our probe curves. Our components are pre-labeled based on the imaging wizard setup. Specifically, we have 3 components we want to unmix: tissue autofluorescence, the 680 probe, and the 645 probe. To begin, select the first pen tool next to the tissue autofluorescence component. Draw on top of the image over the mammary fat pad. If visualization is difficult, deselect Overview, adjust the brightness, and scroll through the different filter pair images. Repeat these steps with the other 2 components. Find the location on the image where each probe is emitting light, and draw over the light emission using the pen tool. The remaining 2 components actually represent the probe plus tissue autofluorescence. We have 2 goals. 1, to separate the 680 and 645 probes, and 2, to separate tissue autofluorescence from both probes. To lend specificity to the unmixing so that the autofluorescence will unmix from the probes, we need to perform component subtraction to generate 3 pure components. To do so, click the Compute Pure Spectrum button. The Compute Pure Spectrum window opens and asks for input. Section A contains mixed spectra and Section B contains the known spectra, or tissue autofluorescence. We will subtract B from A to generate pure probe components. Select the 680 probe in Section A and tissue autofluorescence in Section B. Now name the pure probe at the bottom of the screen. Click Apply. Repeat this process for the 645 probe. After closing the window, the new pure components are now visible in the spectrum list. The software deselects the mixed component and automatically selects the pure component. Note the check marks in the lower left-hand corner of the window. Click Unmix. Our unmixing results appear automatically. Save your unmixing results. After the images are saved and you visually determine the unmixing was successful, save the library by clicking the floppy disk icon. Add an appropriate name and click Save. The library you just saved can be used for any imaging experiment that uses the same mouse strain, probes, and filter selections. You will be presented with both quantitative and qualitative output. For quantitation, the three unmixed components are represented with color maps in the first three windows. There is one image for each pure component. The final window is a composite that includes all three individual components superimposed. Each is pseudocolored based on the selection in the spectrum list area. To adjust the visualization of the composite image, double-click on the image. The brightness, min and max, and color can all be adjusted at the bottom. This view blends pixel intensities, so any pixels that contain a mixture of components will be blended colors. You can copy and paste this image using the Copy tab. Since the pixels are blended, however, we cannot quantitatively analyze this image. To export the results for ease of access later, click the SEQ button. A sequence will be generated which includes the results of all three quantitative images. Click File and Save As to store the unmixed images. Data from longitudinal studies can be easily loaded together from the browser. You would use the Load As Group function described in our previous videos. Analysis on the unmixed images, including drawing ROIs and quantifying results, can be performed as with any other fluorescent image. We will load pre-saved ROIs from the ROI Tools tab. To display the measurements, select the Measure ROIs button. Copy and paste the data into Excel. For our analysis, we will compare data before and after unmixing. To circumvent the necessity of spectral unmixing, you would need near background signal intensity in control animals when the nonspecific filter pair is analyzed. For example, we want to see levels close to the autofluorescence background in mouse number 3, when the 640-680 filter pair combination is used. And we want to see background levels in mouse number 4, when the 675-720 filter pair is used. This would indicate low crosstalk. However, you can see that before unmixing, there was significant bleed-through of both probes when average radiant efficiency is compared to mouse number 1, the autofluorescent control animal. Spectral unmixing will correct for this. After unmixing, the signal bleed-through has been eliminated. Autofluorescence background signal was also reduced after unmixing from 5.95 e to the 7 to 9.19 e to the 5. Now that we have generated our library and tested the efficacy of our probes with a pilot study, we can proceed to a full-scale high-throughput study. Libraries can also be applied to studies where the source is in different locations, for example, a primary tumor or lung metastases. However, the studies must have the same basic design, same probes, same mouse strain, and same filter combinations. Now let's go through how you would unmix new images using a pre-saved library. Select the imaging wizard, fluorescence, spectral unmixing, and epiillumination. Click Next. Click Filter Configuration, and then select by Spectrum Library. Choose your library and click Open. This will automatically load the filter selections from the previously generated library. Acquire your images in the steps described previously. When acquisition is complete, you may begin analysis. Here we have an animal that was injected with our two probes, Ivacins pancathepsin 680 and integrin receptor probe 645. Apply the adaptive fluorescence background subtraction. Confirm the units are in radiant efficiency for analysis. We are ready to spectrally unmix. The purpose of this segment is to demonstrate applying saved libraries. As you proceed through your study, you do not need to regenerate a library for each acquisition. In the Tool palette, open the Spectral Unmixing tab. Under Methods, choose Library. Click Start Unmixing. Select your saved library from the pop-up window that appears. On the bottom left will appear additional information about the library. On the bottom right, choose the components you wish to unmix by checking the box next to the component. Pure components will be selected by default. Select Apply. The results will display as previously described. 1 composite and 3 images for quantitation. The quantitation of spectrally unmixed data facilitates estimation of molecular activity within our tumor, even with narrowly separated probes. It can be used in a high-throughput manner in longitudinal studies to track and record changes in enzymatic activity or expression of particular surface markers. However, any two-dimensional imaging modality will fail to provide an estimation of depth or specific location of the signal source. With 2D imaging, there is also no way to estimate concentrations in absolute picomolar units as the output measured is in photon intensity units called radiant efficiency. If these results are required, We must perform 3D tomographic reconstructions to correct for tissue absorption and scattering at depth in mammalian tissue. Please proceed to the next video in the series to learn more. Thank you for watching.